Aircraft live in an aggressive, changing environment. They move between hot, sunny ramps and cold, high-altitude cruise, get soaked in rain and salt spray, see dust and sand at desert airports, and suffer repeated pressurization cycles and vibration every flight. These combined stresses, thermal, chemical, mechanical, and radiative, interact with materials in ways that lab tests often don't fully replicate. When we design and maintain aircraft, we must think in terms of service environment rather than a single test condition, because real life mixes effects and accelerates damage in unexpected places. Temperature swings are everywhere on an airplane. Skins heat in the sun or at high speed and cool rapidly at altitude, and systems run hot inside panels. That repeated heating and cooling produces thermal expansion and contraction that strains joints, adhesives, and coatings. Over time, thermal cycling can cause microcracks, bondline degradation, differential expansion between dissimilar materials, and accelerated fatigue at stress raisers. Designers mitigate this with thermal-compatible materials, expansion joints, and qualified thermal cycle testing. Moisture moves into aircraft systems by wet weather, condensation, and even vapor diffusion. In composites and adhesives, water is absorbed and can reduce matrix and bondline strength via plasticization and hydrolysis. In metals, trapped moisture in joints or scratches leads to localized corrosion and can drastically shorten fatigue life where salt and pollutants are present. Understanding diffusion, trapped water crevices, and how moisture changes local mechanics is key to predicting life and planning inspections. Aircraft face multiple corrosion types: uniform, pitting, galvanic, and stress corrosion cracking, and each attacks different materials and details. Pitting starts tiny but concentrates stress. Galvanic corrosion occurs at dissimilar metal contacts. Stress corrosion cracking quietly grows under tensile stress and the corrosive environment and can cause sudden failure. Corrosion also degrades protective coatings and fasteners and interacts with fatigue to produce corrosion fatigue, so corrosion control programs, coatings, and proper material pairings are central to structural integrity. Sunlight's UV component breaks down polymer matrices and paint binders over time, causing surface chalking, color fade, and progressive microcracking in polymers and composite resins. Prolonged UV plus moisture cycles can accelerate delamination initiation and reduce surface fatigue resistance. For composite or polymer components, UV-resistant coatings, protective films, and design details that avoid direct prolonged exposure help extend life. And accelerated UV or weathering tests are used to predict long-term effects. Where an aircraft lives changes the failure picture. Coastal and tropical environments accelerate corrosion via salt and humidity. Desert ops blast abrasive dust and sand into joints and seals, causing wear and erosion. High-cycle, short-hop fleets accumulate pressurization cycles quickly, magnifying fatigue effects even if flight hours are low. Fleet maintenance programs must therefore be tailored to base environment and mission profile. Inspection frequency, protective treatments, and repair philosophies all depend on where and how the airplane flies. All of these environmental effects naturally lead into maintenance and aging aircraft considerations. Environmental degradation shortens safe inspection intervals, increases hidden damage risk, and may change the best mitigation from repair to replace and redesign. That's why aging aircraft programs combine structural inspections with environmental monitoring, targeted NDT, and sometimes retrofits. The materials story and the maintenance plan must be written together.